we're more or less on time. So yeah, welcome everyone to Design++, to the seminar series in spring 2024. This is our very first presentation from a lineup of additional 4 presentations that we will have throughout the semester on different topics from computer-aided design, like in this case, to XR and the interaction between machines, humans, and the environment. So I would additionally like to draw your attention to our YouTube website, which you can access through the QR code, for example, or you can also just watch up all the videos that you had that you didn't see before. In addition, I would like to introduce our team. Erica, who's the communication director here, Nijat, doing the camera, and also Erica right now, Fabio and Danielle, who are doing the content with me together and coming up with different topics and presenters. So yeah, let's come to the important person of today's presentation, Benjamin Jones. Ben is a PhD student at the Paul J. Allen School of Computer Science and Engineering at the University of Washington. His research bridges geometry, machine learning, and computational fabrication. He is interested in how to represent and explore complex design spaces. And lately, he's been working on neural representations for CAD geometry and AI exploration of CAD design spaces. The topic of his presentation is representations and learning in computer-aided design. And he will give us an introduction on this topic and discuss how to overcome the challenges of data complexity and scarcity and CAD representations to enable learned analysis of CAD models. So thank you for being here, and the stage and the screen is yours.
Well, thank you so much for that kind introduction. All right, so the title of this talk is Representations and Learning Computer-Aided Design. So this talk is kind of designed like a U itself. So we're going to start out very high level, philosophical mumbo jumbo, like what is design and what is a representation? And then dig down into some particularly successful representations for computer-aided design, get into the weeds with how we can do learning on 2 forms of CAD design, parametric geometry and procedural geometry, and then kind of zoom back out into what I think the future of design representation is. Except today, I don't think we actually have time for all of this, so it's going to be more like a backwards J. And this is my teaser for I'm around all day tonight and tomorrow, so you should come talk to me, and we'll see what the future design looks like. So let's start out with what I mean by representation design. In the most general sense, I take it to mean how we structure a space of design possibilities. So if each dot in this cloud is like a possible design solution to some problem, we could organize it by, let's say, parametrizing solutions with various design axes. Or we could create some hierarchical decision tree to choose between options. Or maybe develop higher level descriptions that abstract away the low level details. So this is pretty abstract. More concretely, representations oftentimes look like how we write down and communicate ideas. So mathematical equations are a representation for relationships between quantities. Machinists might represent parts they want to build as scaled diagrams, while an architect might represent ideas for building as a sketch or maybe as a blueprint. In my work, I am concerned primarily with digital representations, data structures with computable interpretations as designs that can give designers computational support. Many of you are likely familiar with shape representations. So this same duck can be represented either as a bitmapped image or as a triangle mesh or a signed distance field. The choice of representation is important because each confers advantages and disadvantages. So any representation scheme makes some designs possible or impossible, or easier or more difficult to express or think of. And this can be used to one's advantage. For example, using restrictions to remove the burden of considering design constraints. For example, the sign distance field representation enforces the constraint that object represented are always watertight, so you don't need to think about that anymore if you're trying to make something for, let's say, 3D printing. On the other hand, overly restrictive representations can make it really difficult to be creative. We'll see, for example, research mathematicians avoid using computer algebra systems because the strict constraints in their expressions make it difficult to think creatively. All this to say is that the right representation is always dependent on the context you're going to use it in. As an example, let's consider 3 digital representations for knit object designs from the past few years. So the first represents an object as a graph of stitches, the second as connected parametric knitting primitives, and the third as a network of labeled patches corresponding to regions of knit fabric. All 3 representations restrict the designer to only creating knittable objects, which is useful. But the former is best for fine detail specification, the second one exploring large geometric deformations, and the third one, global appearance, is important. So none of them is best, just best in certain contexts. So to figure out what the right representation for a job is, we need to understand this context, which is going to include who or what will be using the representation, how the representation will be interacted with, what tasks will the representation serve, and finally, what are the constraints that exist in the design space that we want the representation to enforce for us. All right, now that we've covered representations in the abstract, let's drill down a bit more on a very successful representation, parametric CAD. So take a look at this scene. Most of the manufactured objects in it started their life as designed in a parametric CAD tool. While there are many in use, they all get their staying power from the representation choices underlying them. So let's see what this looks like. A typical parametric modeling session looks like this. A user will interact with the graphical interface to iteratively build up 2D and then 3D geometry, slowly building up to their final design. I want you to pay attention to this list on the left of features that are being built up. Each of these is a command that is executed when the user interacts with the model, and together they create a procedure or a program that generates the model. Let's break down what this looks like. First, the user is going to interact with the interface. This will modify a CAD program. The program is then executed to generate parametric geometry. More on what that representation is later. And finally, the parametric geometry is then visualized to the user, and the cycle begins again. An important actor under the hood here is a geometric kernel, or CAD kernel. It's a specialized piece of software that knows how to manipulate the parametric geometry representation and is responsible for executing the instructions in the CAD program, as well as generating the visualizations for the user to interact with. At the core of this recipe are 2 representations: parametric geometry and CAD programs. They're interrelated in that a CAD program generates parametric geometry, while parametric geometry is referenced by the CAD program. And I'll go into more detail about what referencing is in a moment. I would argue that these representation choices are what give parametric CAD its primary advantages. The parametric geometry format allows for arbitrary precision needed for manufacturing, while enabling the representation of smooth geometry and sharp features that are common to manufactured objects. It also explicitly contains referenceable substructures that the user can interact with. And having an underlying program allows for the specification of accurate dimensions. Subparts of the program can be locally edited to make design changes without completely remaking a part, and it allows for algorithm control for complex details. So I summarize these advantages of CAD representations as precision, accuracy, and editability. So I just threw a bunch of claims out there, including that referencing is a thing and that it's good. So let's dig a little more into what these representations are and how they work together. First, let's look at parametric geometry. An example, consider this box with a hole. In a CAD system, this object would be broken up into pieces: faces, edges, and vertices. This is what we call the topology of a shape, or its topological entities. And to capture the shape precisely, each entity is given a parametric equation to represent its geometry. These are the equations of surfaces, curves, and points. And these topological entities aren't just floating in space. They have relationships to each other. Specifically, faces are bounded by edges, and edges are bounded by vertices. This is important because equations for surfaces and curves on their own just go out to infinity, so we need to know how to constrain them down to the part we're actually representing. So these boundary associations transitively relate all the entities into a topological graph, which can become clear when we stop visualizing all the geometries and we just see the nodes and links. We call this data structure a parametric boundary representation, or BREP, and it's the lingua franca of the CAD world. One of the crucial features I mentioned is referenceable substructure. And these are the topological entities, these faces, edges, and vertices, as well as a host of higher level structures that are beyond the scope of this talk. And these are the entities which will be directly referenced by a CAD program. Let's take a closer look at that still from a CAD video we watched. So here, a designer is adding a hole to the box by extruding out a circular face into it. This list of operations on the left forms the program that the user defined with the UI, and each line in it is a function call. This pop-up box is letting the user specify the inputs to this function, and here, highlighted in red, it says face of sketch 2. This face is exactly a face in the BREP sense. It's the inputs to operations in a CAD program are references to the generated BREP from the previous stage of the program. So now that we understand CAD representations, let's fit it into our decision criteria for representations. So who? It's built for designers and engineers, and they interact with it using a graphical editor. They use it for modeling, creating manufacturing plans, simulating designs, and a whole host of other technical tasks. And the constraints they really want to enforce are that their designs are precise, accurate, and editable. So looking at the first 2 points of this list, we'll see that there's a representation designed for use by humans with human interaction tools. But what about our robot friends? What if AI wants to get involved in CAD? We should probably first ask if we really want to get machine learning involved here. I'd argue that we do. There are a lot of benefits that ML could bring to CAD. First, we could augment existing CAD workflows. We could build smart autocompletes or recommender systems for CAD systems. And CAD modeling often involves a lot of rote, repetitive tasks that we could learn to automate. We'd also use it to analyze designs or help with reverse engineering tasks. And finally, we could ride the new Gen AI bandwagon and build discovery tools for finding design alternatives. We could also make CAD modeling more accessible with conditional generation, essentially text to CAD. So yes, I think our robot friends get to play too. But what kind of representations do the robots want? Usually machine learning wants data that has a regular structure, has lots of training data available in that format, and it usually wants all the relevant computations to be differentiable so that learning modules can be composed together. Representations we know work well with machine learning are vector embeddings, time series, images, text, and more recently, graphs and even code with large language models. We'll end up using these last two. As we saw, parametric geometry can be seen as a graph, and obviously a CAD program is a form of code. The former will end up being useful for analysis tasks and augmenting workflows, while the later finds its strength in generative and ideation applications. All right, now we're into the weeds at the bottom of this U, where I'll start talking about how we actually do machine learning on parametric geometry and then on procedural geometry. So this part of the talk covers 3 papers that build up a framework and application for learning on top of BREPs. So there are several challenges to overcome when you're trying to learn on top of BREPs. The main challenge is this unique format of a graph of equations being related to each other to build up geometry. And the second is that there's a paucity of labeled training data. So I'll address these in that order. But first, if we're going to discuss how to learn on BREPs, we really need to figure out what do we mean by learning on BREPs? What do we want to learn? So let's remind ourselves of our typical CAD workflow. A user interaction modifies a CAD program that generates parametric geometry to be further interacted with. And we drill it down to the interaction. The point of contact between the user and the program is always in choosing and composing references. So when we want to hook into this workflow, what we really want to do is learn how to reference. So here's what that looks like. We want a system that can take in a BREP, feed it to a machine learning system, and get out individual representations. We're going to use vector embeddings for each referenceable entity in the BREP. And we can later use that in downstream machine learning tasks. So since we know that BREPs look like graphs, we'll adopt the formalism of graph neural networks. For the purpose of this talk, what you need to know about GNNs is that they take as input a graph with fixed size vector embeddings on the nodes and sometimes on edges. Apply a process called message passing that acts over the edges of the graph to update the embeddings at all the nodes and edges, and then finally outputs an updated graph with new embeddings at each node and edge that now incorporate information from the local neighborhood of each. So I'm not the only one to make the observation that GNNs are useful for BREPs. Several prior and concurrent works made a similar observation, and they all use similar pipelines. So given a BREP, they'll first ask the CAD kernel to featurize faces and edges into a vector format, sometimes with summary statistics, sometimes with grid sampling over the surfaces. Then they'll apply message passing over the geometric adjacencies between faces of the BREP to get some sort of final embeddings. So this works for some tasks, but it has problems for our purposes. So first of all, they don't create embeddings for all referenceable entities, only faces and sometimes edges, so we can't really use it as a general purpose tool for learning to reference. The reliance on the CAD kernel for initial featurization is non-differentiable, so these modules can't be composed together. The grid sampling strategy is scale dependent, so small features can be lost and ignored. And sometimes small features are very important, like if you're trying to fix something into a hole. Screws are important. They probably should keep things together. And finally, these things are data hungry. They require a lot of training data to use, which, as I alluded to earlier, can be scarce in the CAD world. So I'll go over all the parts to my solution to these problems briefly, and then we'll dig into each. So first, instead of geometric message passing, we're going to use what I call hierarchical topological adjacencies instead, which is going to allow us for all the referenceable entities to be encoded. Next, we're going to add in the raw parametric geometry definitions to the input featurization, which will remove some of the scale dependence. And we'll even go so far as to only use the raw equations as input, removing the non-differentiable reliance in the CAD kernel entirely. Finally, we'll develop a form of geometric self-supervision to pre-train embeddings on unlabeled CAD data to remove this reliance on massive labeled data sets. So that's a lot. So I'll start with the idea of hierarchical topological message passing. So when I draw it like this, a BREP looks like a really complex graph, but it turns out they actually have a lot of structure. If we reorganize this graph by geometry type, we can see that BREPs decompose into a stack of bipartite graph layers. And this allows us to structure our message passing in one direction up through these layers, hitting each type of entity without exploding our computational complexity. So if we incorporate this change and instead do our message passing in that direction, and also add in parametric geometric equations for some scale independence, we get our first representation learning algorithm of BREPs, which we called the structured BREP GCN. This was applied to two referencing applications, auto-completing assemblies and correspondence matching for collaboration. So I'll start by talking about assembly. So complex CAD objects are actually made up of multiple BREPs that are constrained by reference to operate together. Usually this is done by manually defining each of these constraints in a process called mating, which accounts for about a third of the modeling time for complex models. So the user has to go in, select all the parts and references they want to constrain together, select the type of constraint, and ultimately put it together. This ends up taking a long time. About a third of the time, actually, for complex models. And so what we did is we developed a recommender system that takes in the two parts, as well as rough selections to indicate the user intent, and then suggests the most likely ways to mate them. So that was a lot faster. And that adds up over the course of a long modeling session. So in order to train these networks, we scraped and cleaned a large data set of about 100,000 assemblies and about 500,000 individual mates from Onshape, which is a free-to-use online CAD system, which has the wonderful property that anyone who uses the free version makes all of the data available publicly. So there's a lot of great open source data sets out built off of this Onshape data out there. So here are the kinds of suggestions that we can make. So the user has selected a bracket face and the end of this complicated aluminum extrusion. And from these two selections, our system generates initially over 7,500 potential mates. And here are the top 6 in its ranking. And for the most part, our system wants to align circular bolt holes on each part and in our data set, these two parts are actually mated like this one, the 4th choice. But many more of these are reasonable choices to do. There might be some situation where you'd want this. So we got a CAD expert to validate a lot of our recommendations by saying which of them is there some situation where a user want to use this. So when we see numerical quantifications of accuracy. I want you to think about it as like a lower bound on accuracy. This is the worst we could have possibly done. But there are likely other reasonable suggestions for making above this. So here's what that lower bound for accuracy across all of our test set looks like. On the x-axis, we show how many suggestions are going to be showing the user, and the y-axis is the percentage of the time we presented the correct mate to them. So our system achieves over 72% accuracy, whereas if we compare this to methods using more traditional geometric representations like point clouds, those achieve around a 45% accuracy, which demonstrates the effectiveness of using native CAD representations. So the second application we applied SPGSN to is BREP correspondence matching. So imagine you're designing an engine with a cylinder that must connect to the space. So when designing these parts, the engineer will model the interface by reference to the original part so that if they can go back and edit their design, then the CAD system can automatically update the base so they still fit together. And CAD systems are able to do this because they track the sequence of operations that created each part in order to have robust naming schemes for all the faces and edges and vertices that can be referenced. And this is great and powerful if you're all working on everything in one CAD system, but engineering is usually a collaborative effort. So imagine team A is designing the cylinder and team B is designing the base, and they're all working in their own CAD systems. The problem is that different CAD systems use proprietary formats, so all these useful names and references can't be shared across different systems. Instead, what happens if team A updates their model? So in order to collaborate, team B has to import the model from team A in a BREP format, which is limited to just the geometry and topology. Then references are manually created from the imported model. If there's an update, team B has to re-import the model as a BREP, and the reference engine no longer knows which entities need to be referenced. So then team B has to go back in and re-reference everything manually, and this takes a long time, it's error prone. So what we did is we used SPGCN to train a BREP matching algorithm that finds correspondences between faces, edges, and vertices of two BREP models that allows the reference engine to automatically update references and propagate their updates. So people can just share updates to CAD models between systems and it will automatically update to the new models. In order to train the system, we mined the dataset we had previously collected and generated a bunch of synthetic edits for which we already knew the correspondences, as well as getting an expert to mine out some true variations to do some validation. So here's what correspondences look like. What we're looking at here in the blue, red, and gray is a diff of the two parts merged on top of each other. And then we are looking at our correspondences, where correspondences are done by corresponding colors versus the ground truth. And anything in the blue-green spectrum means we got it right. Gray means there shouldn't have ever been a correspondence, and beige, which you'll see one little circle over there, is something that we could have matched, but we didn't. And I want to point out that if we could have matched something that we didn't, we've just gotten back to the base condition if someone has to match something manually if it's used in a reference. So that's no harm, no foul. That's an okay situation to be in. The situation we really don't want to be in is making an incorrect match between two BREPs, because then an erroneous reference can be made that will be a silent error to the user. So it looks good, but how do the numbers actually look? So quantitatively, we measured 5 categories. Like the true matches, how many things should have matched we matched. Correctly unmatched entities, those entities we could have matched but missed. Faces we matched the wrong entity, and faces that should have been unmatched but we matched to something. So basically, blue is good and helpful, beige is no harm, and red are harmful results. So if you look this up across all the topology types, we get around 90% correct with about a 2% error rate. And this error rate is tunable, so we chose it to be 2%. We could have chosen it to go down almost all the way to 0 at the cost of going back to a few more mismatches. But these results are also on synthetic edits, and you might ask, okay, does this process of just generating random edits actually work in the real world? And it turns out, yeah, it does. So we had an expert user go in and find a bunch of cases of actual re-imports in the data set. And when we evaluate our metrics across those, we get very similar numbers. So we're confident that this system of correspondence matching will actually scale to real complexity CAD systems. And in fact, these numbers are better than the systems that are being currently used in commercial CAD systems. So we're hoping that they will be adopted in the future. Cool. So those last two examples I showed were some of the few where a lot of labeled data is available, either through finding it in the wild or synthetically generating it. But in reality, most labeled CAD data is for the proprietary data of engineering firms. And creating a new data set from scratch is really expensive because there's a ton of expertise needed to use CAD systems. Hiring a bunch of engineers to label a ton of data is A, very expensive, and B, engineers really don't want to do it. We've tried. You get maybe 20 out of them and they go home. So we need a different way. We don't have a lot of labeled data, but what we do have is a ton of unlabeled CAD data, all of this raw geometry in the wild. So what can we do with that? Let's go back to our representation learning pipeline for BREPs. The next thing we said we would do is add geometric self-supervision. What do I mean by that? Recall the anatomy of a CAD program. Since BREPs are such a complex structure, they require a CAD kernel to interpret and visualize them. What if instead we trained a neural network to do this and used that as the self-supervision loss? We could then kill two birds with one stone there, having a solid goal to train self-supervision with and removing the remaining dependence on a CAD kernel. So our self-supervision model looks like this. We train an encoder-decoder architecture to take a large unlabeled data set, create a vector embedding for BREP patches, and then decode them using a novel bounded patch functional representation that I invented for BREP geometry. If we add this to our solution, and then also remove the final kernel dependency featurization, we get the full picture. And then once we have these embeddings for BREP faces, we'll use them to learn new task-specific decoders for useful problems from very little data. So these task-specific networks are very small and lightweight. We do no fine-tuning of the encoder, and they do not require the sophisticated algorithms from the CAD kernel for either training or interface, which both makes them much faster and makes them fully differentiable. So we can compose them together. So one benchmark we tested this on is segmenting a model based on constructive operations like extrude or fillet that was used to make each face. This is a useful first task in reverse engineering. So if you have a model, you have a BREP model, you want to get the program out, you'll often always want to figure out, okay, what were the program operations that I used to create the faces, and then use those to try to build up a program. So our system produces results that visually look almost perfect, but let's quantify that. So we trained many instances of our network and several baselines using successively smaller and smaller training sets. So what you're looking at here on the x-axis is training set size, from down to showing it only 10 examples to showing it 23,000 examples. And on the y-axis, you're seeing the segmentation accuracy. And that band is a confidence interval, so it shows how much dependence there is on what particular examples you're showing it. So if we compare to existing methods, our Chink is achieving significant performance improvements both in few shot and also produces more consistent results. So let's look at, let's say, results with only 100 examples for our method on the second row versus some of the baselines. And you'll see that that 40% accuracy they were finding was really them just figuring out what is the most common operation. So most things in CAD are created by extrusion, which is not really surprising. But even at just 100 examples, we're able to pick up a lot more of the types of operations. So looking back at the plot, we'll also notice that our method achieves the state-of-the-art results even at full data, which is impressive because these other baselines are really much larger networks. They're trained end-to-end with access to the CAD kernel, so they are able to do sampling. They're able to do get all these other statistics, whereas we're just using the raw parametric geometry equations and nothing else as our input. And if we look at how long it takes to train these things, ours is the blue one at the bottom, we'll see that this method is order of magnitudes faster than prior networks. So you can train one of these networks in seconds, which lets us envision using this for on-the-fly training during CAD modeling sessions. So I like to envision something like flash fill from Excel, but for CAD. So you start doing a couple operations and it figures out what you're doing by training one of these cell networks and auto-suggests the next operation you want to try. And finally, I'd like to highlight the green curve here. So that's the only other prior self-supervised BREP learning approach that uses contrastive learning instead of this geometric self-supervision. And this striking dissimilarity in performance emphasizes to me at least that using the geometric self-supervision is really important to getting this sorts of performance. Somehow learning to be a CAD kernel means that you have to encode all of the relevant information in your embeddings versus just learning to distinguish between similar graph structures. Yeah. So this architecture also allows for more than just segmentation. Despite it not being trained on whole BREPs, it was able to perform zero-shot part retrieval. This could be useful, for example, if you're trying to suggest replacement parts from a large catalog. You can look up by a BREP and get other similar ones. Also, since it is fully differentiable, it opens the door to gradient-based BREP optimization. So here we just did a very simple test where we took one BREP and we fit it to a new point cloud and let it optimize the parameters of the underlying geometric primitives. So I think with these kind of pre-trained kernel-independent methods, we can get a lot of really interesting applications in the future. All right, so that was parametric geometry, but there's a whole other side to CAD representations, which is the code side, the procedural geometry. So lately I've been focused on neurosymbolic approaches using these programmatic representations of CAD models. So I'll talk about recent work that learns to reparameterize CAD programs, and then I'll touch a bit on ongoing work in applying language models to CAD generation. So let's start with the reparameterization work. So the promise of parametric CAD modeling is that you can just make one model and then be able to explore a whole bunch of different design alternatives by varying parameters. But this is really kind of a false promise. It has a lot of problems to it. So the first problem is with editing. So which parameter should you use? Let's say I want to increase the height of this block. How do I know which of the parameters do I have to change? I would have had to encode that when I was first making the model and know, this is something I want to do in the future, so I will make a parameter for it, I'll name it height, I'll know that's the right one to do. Another problem can arise with under-constrained models that are very common. So there's no guarantee that a parameter will move everything that you would expect it to. Let's say I wanted to move the leg of this chair. Unless I had specifically made my model to widen the base of the chair when I do so, I'm going to create something that looks decidedly unchair-like all of a sudden. So I'm going to make maybe, I don't know, a controversial part. I think that CAD is actually bad at iterative design because making a good parametric model is hard and it requires foreknowledge of all of the desired variations. Whereas in a real design process, you're going to figure out what you want as you go along. But what if instead we could just take a CAD model, throw it at our nice robot friend here, and get out a model with all the variations we could possibly want? That'd be pretty cool. I'd like to see that. So that's what we tried to build. We call it reparam CAD. So this is a buzzword soup. We take a large language models and large image models and symbolic reasoning, we mash them all together. So the key insights here is that the large language models and the text modules can encode a lot of semantic and shape understanding. And with symbolic reasoning, we can remove stochasticity and noise from the models we get out of these machine learning models and also add some interpretability. So how does this work? We start with an input CAD program and a text description. So the first thing we're going to do is take that text description and feed it to a language model to generate a whole bunch of text prompts describing variation. So we might, for example, ask ChatGPT, what are different types of chairs that exist in the world? And it will come back and say, oh, there's benches, there's chase lounges, there's rocking chairs, stools, wingback chairs, etc. We'll then, for each of those text prompts, use stable diffusion and differential renderer to slowly modify our CAD model to match the prompt. So we have here morphed that initial input chair into models that look more like each of these prompts. We will then use a symbolic process to do constraint discovery. So we are going to take each of these and figure out constraints. There are things like, well, the legs are the same length, width, and depth, or the legs attached to the bottom of the seat, or the backs are attached to the top. And we're going to look for constraints that are shared between all of these. And these do two things. First of all, it figures out what are the constraints that kind of define the class. What are the things that make a chair a chair? And the other thing is it removes noise. So you'll notice in that process of optimization, you have a lot of little noisy artifacts, like the legs are sticking slightly out of the top of the seat. That can't be comfortable. But like across all of the chairs, most of them mostly have the legs underneath the seat. And so we figure out that's a thing a chair should have, and we apply that. So using these constraints, we can reparameterize our model and make a new one that adheres to all these constraints. So it'll always be a chair. And it gives you nifty little sliders that let you go between these different variations. Or if you'd like, you can have it be a reduced set of your original parameters. But it essentially gives you a reparameterized model with some semantic interpretation of what these parameters mean. So we applied this to several different models, chairs, cars, cameras, bottles, and tables. And the results all look pretty reasonable. This was a small pilot study, so we used a kind of reduced CAD language of CSG with Union. There is, however, a bunch of ongoing work on how to do differentiable rendering in more complex CAD geometries. And so we think that this basic framework can be applied to more real-world scenarios in the future. All right. And finally, I'm going to talk a little bit about ongoing work doing in generative design for CAD models. So we've all seen pretty amazing things from generative AI. So for example, here I can start with the description of an item I want and get a picture of a shoe rack, and then decide, nope, I want it to be a little different, so I can go in and manually sketch on it, feed it back to a generative AI model, and get a new design from it, which looks great. I would like that shoe rack. I mean, maybe it's a little angled, but otherwise pretty good. However, even if this were in 3D, it wouldn't be fabricable. There's no way you can build this thing because it lacks the three key properties of CAD representation. It's not precise, it's not accurate, and you can't really go back and edit this without the model maybe completely redesigning it for you. But these are all the properties that we know are enforced by default if we use CAD representation natively. So can we instead generate directly into a CAD representation and take advantage of this forcing function and constraints? Can we say something like, oh, design me a shoe rack that looks like this picture, but it's 3 feet tall, has 4 shelves, and angled like this sketch. Throw it through an multimodal model that gives us out some code, and that code generates a nice fabrical model of what we want. That's the dream. The first question you might ask is, LLMs are kind of magic, right? Can't they just do this? They should, right? Last summer, a group led by Wojtek Matsuik and Adriana Schulz explored the capabilities and limitations of LLMs in design and manufacturing, and I spent last summer at Adobe exploring various models' abilities to generate CAD programs. So I worked with GPT and flamingos and llamas, all of the animals. And then we can summarize what we found as LLMs know semantics but not geometry. So they can describe object decompositions, they can write syntactically correct CAD programs, and they can generally make local geometry that's pretty good. But they really can't spatially compose objects. Like it'll try to make a dog and it will say, oh, there's a tail and there's some legs and there's a head, but it will look like some very messed up Picasso with everything all over the place. But this can inspire a solution. So based on the observations, I'm attempting to make a CAD language designed to be used by LLMs. So what it does is it decomposes objects into meaningful describable parts with semantic names. And it describes the geometric relation semantically rather than numerically. So instead of saying, this is coordinate x is 0 and the coordinate of this x is -3 to say something's to the left of it, you just say this is to the left of this. And then it relies on a solver to make the geometry correct. So I can kind of use this electrical socket as an example. So an LLM can be good at decomposing this into knowing what the different slots are, what the faceplate is, and it can list me out all of the kinds of constraints that are going to be around it. It also is able to generate basically the sketches for each of the subparts. This is what I talked about being good at generating local geometry. And then I use a solver to make sure that I'm placing everything with the correct geometric relationships overall. So this is still a work in progress. This is an example of kind of thing it can generate so far. I've been targeting laser cutting as the fabrication choice. So it's generating 2D sketches embedded in 3D. And so here we'll see it's trying to cut out a circle for the disk of a sundial. It's using blue as engraving lines that it's making to engrave the hour lines. And then it also can create the gnomon, the triangle that cast the shadow. So that is what I've been up to right now. And here is the point of the talk where I would talk about the future of design representations, but I was told I had 30 minutes and we're at 40. So I'm gonna use this as a teaser now. So I am out of time for today, but I'll be around tonight and all day tomorrow. So please come find me to chat about what's next, or if you're not around or if you're online, please drop me an email, benjones@cs.washington.edu, and I'll open it for questions.
Benjamin, thank you very much for this super interesting presentation. Yeah, we would follow up with some questions. Yeah. Do we have some first ones? Else I'll open up. Yeah, so generative design is the future in this area.
Partly, I think. I think generative models are really interesting because to me, they model a lot of the way that mathematically that I think the design process works in our head. So I think about design as this process of taking this big cloud of possibilities and kind of figure out what you want and slowly narrowing down on a solution. And if you think about an autoaggressive generative model, what it's doing is it has this big distribution of possible designs, and it's slowly contracting a probability distribution over what those designs are. And so it kind of seems it's very synergistic to what we're doing. And so I think they're very interesting for actually expressing partial designed intent. So I'm really curious to explore how can we more effectively interface with these in kind of in a collaborative way, because I feel like they look more like how it interact with the person. Like I'm expressing a partial design intent, and you'll kind of get the idea. So I do think that that's kind of the role for generative design, but I don't think it's the whole future. I think we're still going to need tools that allow us to very specifically specify and poke and prod and make exactly what we want. Because ultimately, like while there are these, just the distribution the model has of just possibilities and distribution we have in our head, ultimately we still have to communicate what the exact final design is, and that's going to be always, I think, the role of precise tools and expert tools.
Yeah, that's true. And yeah, I think it looks extremely promising because, like the structures and the models that you showed are relatively complex for civil engineers and also architects. So I think it's super applicable for the current structures that we have, like the columns. I mean, they're rectangular or hollow sections. So this is something that could be, I think, directly applied also in civil engineering applications.
Yeah, I think for some of those situations too, you are in a situation where you can pretty easily write down what the constraints are that you need for things to like stand up or to interface properly. And so if you can write down those constraints, you can create a language to generate, a representation or language to generate it in such that anything you generate will at least fit those structural requirements. And so I think then you kind of are left to letting the generative part take over the aesthetic part, which I think is what existing generative stuff is much better at already. So I think that's almost at the point where you could probably start doing stuff like that pretty well.
Yeah, interesting.
Thank you very much for this very inspiring talk. I'm actually curious, how did you implement your systems? Did you build on a commercial CAD system?
Yeah, so initially the system was built on top of the Parasolid CAD kernel. So like the mate recommender system is built on top of Onshape with a Chrome extension basically. So it would kind of sniff where you're clicking in the model and then pop up the recommender system. You click it and it would use, Onshape has an API, so we're able to hook into that. For the correspondence matching, that was implemented, that is again implemented on top of Parasolid, but we don't have a UI for that one. So we were actually in collaboration with Onshape on that, and they do have an internal system that uses a fully heuristic version to try and do that matching. And so we were just building kind of the back end with the hope that in the future they will adopt that and use our learning on top of that in the back end. So we didn't actually build an interface for that one. And then for the self-supervised stuff, that's actually built on the open source CAD kernel, Open Cascade. So when we started working on that, I actually recruited a really talented undergrad who helped convert all of my Parasolid code into Open Cascade code. So we now actually have an open source version of this well, we always had the open source version for Parasolid, but it was open source, but getting a license for Parasolid, the price is, if you have to ask, you can't afford it. It literally took us a year of begging them for them to give us an academic license, so no one is able to use that. But now we actually do have an open source version that everyone can use and uses just free software. So it's out there.
Thanks, and maybe a follow-up question to this. So you mentioned differentiability a couple of times, and one challenge is that the CAD kernel is not differentiable, right? So you came up with a couple of really neat ideas to circumvent this. I mean, another solution would potentially be to really work on a differentiable CAD kernel. I mean, is this something to think about? Should we look into this, or is this a bad idea?
That it is an interesting idea. I think it is a good idea to some extent. Like, people have tried making differentiable CAD kernels before. People have succeeded in making differentiable CAD kernels before. They're just very, 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 very slow. But that's partly because CAD kernels are these really big, old monolithic programs that have 20 or 30 years of kludges built into them for all of the special cases that come up with geometry. And so I think if you go ahead and try to build a differentiable CAD kernel from scratch, you're going to not get as much adoption because it's always going to be missing that one feature that somebody wants. And it's always going to be not working in certain edge cases. Like, even the open source CAD kernels out there have the same problem where they can't cover all of the weird edge cases that happen when you have a fourth order NURB surface intersecting with a third, and like all of these crazy things that happen all the time, right? So I think that, short story is, I think, yes, we should be looking into that, but I think that is going to be more interesting for the applications where we're not trying to interface with existing systems.
Okay, thank you. Do we have more questions? Oh, yeah. I mean, you will be the next one.
Yeah, thanks, Ben, for the talk. I'm very excited about the reparameterization using ChatGPT. And I noticed as part of your input, you have the a skeleton program already there. So from my understanding, it kind of constrained the topology of the final generation. So for example, now I want to generate some chairs with like 3 or 4 legs. I mean, you need to change the topology somehow. And do you think there's a way to do that?
Yes, I do, actually. That was a proposal I was just trying with Bernd, is about trying to do that. But I think that we can use program rewriting to do that. So there's a lot of good techniques that have been developed for compiler optimization that are essentially writing programs that are equivalent in some sense. And we can define equivalence to mean, for the current set of parameters, this new program can produce the same output geometry. And so we could try to find equivalent programs that have the ability to generate different topologies. So have, for example, a parameter that controls the number of legs. And there has been some work on kind of getting part of the way there. So like taking programs that have a bunch of repeated elements and recognizing, using these kind of compiler optimization techniques, that there are repeated elements. So like an example in one of these papers is they're designing like the wheel of a ship that has a bunch of spokes coming out. And in the initial design, that was a CSG tree that just had each of those spokes individually made. And the compiler is able to recognize, like, oh, this is effectively an unrolled loop. Let me re-roll into a loop and discover this parameter. So yeah, I think using techniques like that, we can start to figure out ways to make the topology edits possible. And the other thing I think is interesting there with language models is to control these compiler optimizations, really, you need to have some notion of what your objective is, what you're trying to get it to do. And it's really hard to write down the objective function, let me make a 3-legged chair. Like that's mathematically difficult to do. I think that's another place where language models are really interesting, because they allow us to write down the sentence, this program lets you make a 3-legged chair, and then they give you like a numerically available probability distribution that says, this program is more likely to be able to express a 3-legged chair than this program is. And so you could actually use that as a discriminator when trying to generate topology variations, or even just variations in program structure is what that really comes down to. So yeah.
Cool, thanks.
Mm-hmm. Yeah.
To your knowledge, for like some of the more common engineering CAD softwares, how different are these CAD kernels?
They are fairly similar. I don't have access to a lot of them. Parasol don't. I've really been able to play with myself. They all tend to have a lot of the same, like the core features. That's really the same in all of them. They all have different extensions to them. So like the sketch, extrude, revolve from 2D stuff, like the base for all of these things. And then over the years, basically all of them have added booleans on. But some of them have, for example, like lattice structures. Parasol has it. I don't know if all of the other ones do. They like all of these kind of like special generative methods. They'll add in. So they each try to like add in special sauce. But like at the core, they all look very similar. At the core, they're all operating on breps and using references. And then there's a whole other layer in that the CAD kernel is separate from the CAD software, and so the implementer might use it differently. And so,
proprietary typically for some of the big ones?
Yes, almost all of them are proprietary. Yeah. There is one open source one, which is called Open Cascade, which is used in FreeCAD. But otherwise, every CAD system out there uses one of the proprietary CAD kernels. Either they are buying it from someone else or they're developing in-house.
Can I ask one more question? I mean, regarding this like chair question, has it been kind of thought to just latch this onto some kind of basic simulation of like a mechanical simulation that like this chair allows for somebody to sit on it, will tolerate the weight, and then you can basically kind of reinform, essentially your model that this is actually a valid structure or not, no?
Yeah, so there are some works that are doing kind of simulation going from simulation back into design. Generally, those don't work on CAD representations. Usually those are working with things like meshes and things that are more like easily different, like you can use differentiable pipelines to like push back all the way to the raw vertex positions. Because what gets really tricky when you're using CAD representations is because you have these discrete structures that they're just hard to do optimization over. And so, yes, people think about it. No, I don't know of anyone doing it on like real CAD geometry.
Okay.
So I think we have time for one more question, Anton.
Okay. Thank you. Thank you for the great talk, very interesting work. My question is about the ongoing work with the language model. Yeah. What were your reasoning behind the choice to develop a custom designed DSL language for like LLM-friendly language as opposed to leveraging the capabilities of language models to operate in known environments, like NVIDIA research used LLMs to customly build tools and extend environments in Unreal and Minecraft. And then the premise is that these models and also the new ones that will be coming, they have seen data on existing environments. So what was the reasoning behind the choice for DSL?
We did some tests with using existing languages versus like defining our own DSL and use it. And like, honestly, it does just about as well with using an existing language as our own DSL. The other thing was that these kinds of constraints I'm talking about, like, like what I'm calling these kind of layout constraints, like, oh, this is the left, like, the legs are under the chair, for example. That is actually not something that's expressible in traditional CAD software. So most existing CAD systems, for their constraint systems, only allow for equality constraints. But like the notion of something being underneath or to the left over, like, inside the bounds of, are inherently inequality constraints. And the solvers built into existing CAD systems just don't handle those. And so we're building a language around those kinds of constraints that existing CAD systems just don't handle. The other thing that building our own language let us do was give very fine control over a feedback loop to the model. So one of the ways to get a model to generate this code effectively is when it does something wrong, we need to tell it. Mm-hmm. And by having complete control over the language interpreter and runtime, we can make really fine detailed error messages back to the language model that can point to like exactly where in the code something went wrong, exactly what the error is. Whereas if we're using an existing system, those things might not be exposed.
Yeah, I think we can lead over to the apero. Benjamin, thank you once again for this nice presentation. I think there were a lot of questions and a lot of interest on this topic on generative design with CAD models. So this will give us the basis for ongoing discussions. I would like to promote our next guest speaker, Daniela Mitterberger, who some of you or most of you should know. She left us and went to the Princeton University and will give a talk about strange comfort, intuitive machines, and robotic gardens, where she will explain the behavior between machines, humans, and the environment. Thank you once again, and enjoy the apero.
Thank you for having me.